Hello, Code Adventurers. Welcome to day 17 of Advent of Code 2023. Let's dive in and take a look at the problem. Day 17, Clumsy Crucible. Our lava starts flowing rapidly once the lava production facility is operational. We descend, and we get a view of Gear Island, and we see what we had trouble finding on our way up. Half of Gear Island is empty, but half below you is a giant factory city. You land near the gradually filling pool of lava at the base of the new lava fall. Lava ducts will eventually carry the lava throughout this city, but to make use of it immediately, elves are loading it into large crucibles on wheels. The crucibles are top heavy, pushed by hand. Unfortunately, the crucible becomes very difficult to steer at high speeds. From the lava pool to the machine parts factory. To do this, you need to minimize heat loss while choosing a route that doesn't require the crucible to go in a straight line for too long. The elves have a map. That's our input. Hundreds of other parameters are used to calculate how much heat loss can be expected for a crucible entering any particular city block. These are our city blocks. This is the heat loss in each of those city blocks. Because it's difficult to keep the top-heavy crucible going in a straight line for very long, it can move at most 3 blocks in a single direction. It must turn 90 degrees left to right. The crucible also can't reverse direction. After entering each city block, it may only turn left, continue straight, or turn right. One way to minimize heat loss is this path. The path never moves more than 3 consecutive blocks the same direction and incurs a heat loss of only 102. Directing the crucible from the lava pool to the machine parts factory, but not moving more than 3 consecutive blocks in the same direction. What is the least heat loss it can occur? Here we are with another grid problem in Advent of Code. So that's pretty straightforward. This is a pathfinding problem. So we can use Dijkstra's algorithm, and we'll need some sort of priority queue. Really, you can look at this as just a set of nodes, and the 4, the 2, the 3 here, they're the weights to connect those nodes. So we'll use a heap, and then with the heap, we'll use a priority queue. With the priority queue, we'll use the heat loss calculated summative from the start position to the next node to the next node, and we'll determine what node we check next by that. So let's just load our test data. So we got our input. It's a grid, and we have to walk this. We're going to use Dijkstra's algorithm with a priority queue to get from point A to point B. Let's look at implementing that. We're going to use a heap and a priority queue. I'm going to create a heap. Go has a heap. So we have a city block, heat loss. As a row position, a column position. We could do this all in one line, but I don't want to. The heat loss will be our priority. There are 3 other things we have to record here. A row direction, a column direction. So I'm going to change from the last method I used, and what we'll place in row direction is if we're moving up and down rows, it'll be a 1 or a -1, a 0 if not. And then for the column direction, the same thing. It'll be either 1 or 0, or a -1 or 1, and a 0 if not. And we should never really see where row and column are both values. You're either going to have row direction set, or column direction set, and we'll control that. But that way we know what direction we're heading in, so that if we can keep moving in a direction, we can keep moving in that direction. The last piece to this is, if we look back at our rules, we can only run in a straight line for 3 blocks. So we'll just call that count. This is a struct. Do we need that public? I don't think any of these need to be public. In fact, I'm going to change that. I always find it best with structs, if there's not a need to make them public, don't. Methods as well. All right, so that's set. We got our city block defined. Let's define our priority queue for that. So we're going to create a type called priority queue, which will be a slice of a pointer to a city block. In order to implement the heap interface, we have to implement a couple of methods on our priority queue so that we can implement it as a heap. So we need a length. We need a less method. So we're comparing heat loss in this comparison. We need a swap function. So what does it look like when we swap items as we're sorting? So we'll swap their values and then update their indexes. We need to typecast this as our city block. And then we need to append it. All right, and then finally, how do we get things off the priority queue? So we're going to take the last record on olds from the city block. We're going to nil out that last record. We're going to set the index to -1. And we're going to essentially copy and replace PQ with the previous PQ -1. And then we're going to return our city block. All right, and then one last thing. Let's just try to implement our heap now. All right, I think we satisfied the interface. So now that we have our heap created, our next step will be to start placing things on the heap. We're going to start by, let's do it this way. All right, we're going to init our priority queue. This should be a pointer. We'll do that all the time. It'll just be easier to reference it. And then we're going to push our initial value. And so the value we're going to push is our city block. Our first city block is going to have a heat loss of 0 because it's our starting point. It's going to have a row of 0, a column of 0. Our direction is going to be nothing. Our count is going to be nothing. And I don't think we need to define the index. Let's take a look at what I did here with Heap. When we add something, we always set the index. So it's kind of arbitrary. I guess to do this a little bit more correct, I think we would prefer if I did row, column. Oh, heat loss. That's what it was. Yeesh. Heat loss. Row. Column. Row direction. Column direction. And count. Yeah, I'm just not a big fan with structure like that. So we're going to go with this here, I think. And then I think like that. I realize it's a little bit more verbose, but I feel like this better defines the structure. All right, so now that we've done that, we've got our initial thing on the queue. Okay, we're going to loop until our length, our priority queue length is 0. And so now we get into the meat of the traversal. If we're starting here at the 2, then there's only 2 ways to go. We can go down and we can go right. So what we're going to do is we're going to say for dir. For direction, I guess we could just call it out. We'll do D instead. We're going to do a slice of int. And we're going to define each of our directions. So that would be right. left, down, up. And so those are our directions. And then we will say, because we know we can't go backwards. So if we got to do one more thing, city block equal to heap dot pop PQ, right? But then this has to be cast as so if we go back to our heap implementation, it's a city block, right? We'll call this new row and new column. So new row is going to be our row, city block dot row plus d sub 0. Because that is the first position, which will be our row. And then our column will be that. Now, if new row so if new row is less than 0 or new row is greater than length of grid minus 1 or new column continue. So what this will do is this will protect from us going out of bounds. If we're out of bounds in either the X or the Y, we don't want to go out of bounds again. We have one more check because there's a requirement that we don't go more than 3 consecutive in the same direction. We'll call it count, and it's going to be city block. We'll count as 1, and we'll say if city block dot row direction equal d sub 0 and city block dot column direction equal d sub 1, then C equals city block dot count plus 1. So if the city block row direction is the same as the column direction, so if they're the same, we'll go ahead and increment from whatever the count was because we know we're heading in the same direction. And if C is greater than 3, we continue. The reason we're doing that is because we're allowed to move 3 consecutive in a given direction. And we're going to start at 1, then 2, then 3. If that fails, then we come back to 1. Or if we exceed that, then we know we can't move in that direction. So for instance, if we're starting at 2, if we go to 4, 1, 3, well, the rules say we can't go to the 4. So we're just going to skip that one and not put it on the queue. Now we could get back here if we go to 5 and then 4 and then 4. It's a valid path, but we can't go straight to 4 in a straight line from 4 to 4 here on the right side. All right, so now that that is in place, the next step is to push these onto the heap. So heap.push our PQ, and then we're going to create a city block similar to the way we did earlier. And the heat loss We'll go and copy this down here. Whoops. It's okay. We'll do some abbreviation here. I didn't realize I smashed my variables. All right. So our heat loss is going to be our city block dot heat loss plus CV. Sorry, let me change the name. Plus the heat loss of our grid in our new row in our new column. Okay, I don't have a pretty function for that right now. We can come back to that later if we want. So this should, here, we'll print it the not so pretty way. I honestly don't know how that will look. Oh, well, whoops. That's not what we want. Yeah. So that test is running, but it's not going to finish. Okay, there we go. Not great, but not terrible. So we still have our grid, so that's fine. We have what we need to proceed. We should really create I'll work on creating a pretty function for asGrid I. Actually, let's just go ahead and do that now. So grid I is just an int representation of the grid. I mean, this will work for now. Maybe we come back to it later. I don't want to spend a whole lot of time on my debug. Right. We'll add the panic back in. And we run it. Panic. All right, let's do it. All right, that's good enough for now. So now we have the grid printed in case we need to look at it, and we can keep running with it. So back to our actual solve here. So we're going to push the heap. We're going to set our heat loss to whatever the previous city block heat loss is, because we want it to be additive, meaning the total cost to get to this particular location at this time. And then we're going to add in the cost of where we're headed. The row is going to be the new row. The column is going to be the new column. The row direction is going to be our d sub 0. And our column direction is going to be d sub 1. And our count will always be C, which will either be 1 or if we're heading in the same direction, it'll be an additive of that. There's one other check I almost forgot. We can't go backwards. So new column cannot be equal to city block or CB dot column, and new row cannot be equal to CB dot row. If this is true, we also continue. And we can probably move that one just as far up to the top before we go any further. I kind of like to think broader to more scoped as I do some of these if continues. All right, so this is our new heap. What is going to prevent us from reprocessing from the same position in a loop? Like once we've seen something for the first time, I guess what matters there is not only the row and column, but the direction and the number of counts that it took to get there. I don't know if we need to do a scene. Let's do one last thing here. If our city block dot column equal to, let's do row first. I always like to do row first. If that equals to our length of G minus 1 and our city block dot column equal to length of G sub 0 minus 1, then we can return our heat loss. Is that good enough? What's the value for this is 102. Okay. Just create a map called visited, and we'll just do a string and a bool. And every time we come through here, we'll do a key. Oh, weird. Oh, because the thing finished. Yeah. All right. Oh, we'll do a key, and that key is going to be we don't want to do the entire city block because we don't want the heat loss to be in there, because when it circles back, it's going to be pretty obvious. So we'll do cb dot row, cb dot column, cb dot row direction, cb dot column direction, and we'll do cb dot count. So it'll give us an idea of, just to make sure that as we revisit this node from different directions, we're properly represented here. And so we'll say if we find this key inside our visited, we'll continue. And then otherwise, we set it. So, oh. All right, well, we're getting close. I don't need all of these prints anymore. So let me get rid of that. Do I? Let me run it again. Hold on. It's going to be the previous node. So this check's not actually working. What we need to make sure is that it's not the reverse. So the way we can make sure it's not the reverse is if we've got D0 cannot be CB dot row direction, the inverse of that. So the opposite of and at the same time. Let's do it this way. Yeah, the inverse, and then column direction. The inverse. So not equal, inverse. Okay. So what we're saying here is that if our row direction and our column direction are the opposite of the direction that we're heading. So if we're going, you can imagine if we're going to the right, these would both have to be the inverse, which means we're going left. And so an inverse of 0 is still a 0, but that'll allow us to check both of these at the same time. And then, because I think what's happening is we're going in the inverse direction on one of our test cases here. Ah, okay. We're gonna change this because I didn't like this earlier, and it just kind of bit me, and so now I'm gonna fix it. We're being a little bit verbose today on our names, but the issue I ran into is here, in that these were both pointed to row, and this one was the one that was the issue. Yeah. All right. Even though it's still like, if we're headed in the same direction, these don't really change it, but fundamentally, yeah, okay. Test passed. So let's run. Let's grab our input. Let's put it in our file. $843. Awesome. Part 1 done. Let's move on to part 2. Part 2. The crucibles of lava simply aren't large enough to provide an adequate supply of lava to the machine parts factory. Instead, the elves are going to upgrade to ultra crucibles. Ultra crucibles are even more difficult to steer. Once an ultra crucible starts moving in a direction, it needs to move a minimum of 4 blocks in that direction before it can turn, or before it can stop at the end. However, it will eventually start to get wobbly, 10 consecutive blocks without turning. Okay, so we've got a minimum now of 4 blocks in a given direction and a max of 10. So let's take our current function, if you will, and let's just augment it with 2 inputs. We're going to call it min and max, and they'll be ints. And for this one, the min distance was 0 and the max distance was 30, right? Whoops. 0 and 3. Okay. And so now, if we go to our tests, and min, max, ints, and we'll call it min 0, max 0, or sorry, 3. And we will call this test.min, test.max. All right. So now we come back here and let's implement those. This should be pretty easy. This is just min, max. And how do we want to implement min? So we'll go ahead and add an else here. I think it makes sense. So that's anytime the direction doesn't match. If C is less than min, then we continue. And this should get us to the next record. Now I think there's one other change we'll need to make. Here, we also need to make sure that our count is greater than or equal to our min, because we can't get to the end and not have our minimum values, right? So our min is 4 and our max is 10 and our value is 94. I think that will satisfy. Not too bad for execution time. Let's see if we got our answer right. Curiously, it's the right answer for somebody else. Well, there we go. Okay. So, last little problem here is we could be equal to the minimum here. All right. Let's run this again. Awesome. Excellent. Finished day 17, Advent of Code 2023. Let's do a quick recap, get rid of this, and we'll start from the top. So part 1 solution was pretty much part 2 with some additional parameters. So I modified my part 1 function to implement part 2, and I did it in such a way that those parameters could be tweaked. I may utilize that in the future. That's just the way I chose to do it. I have this function here called asGridI, which just gives me a grid of int events or a slice of int events. We created a priority queue using a heap. So we go back to the actual problem here. And, we have a grid that is essentially a heap map, and our goal is to get from the 0, 0 position to the end row column position. And the numbers in this grid represent a heat loss map or a cost. And the higher the cost, the less likely we want to go there. So we implemented a Dijkstra algorithm using a heap map, a heap in Go with a priority queue. And we use the loss amount as the cumulative score to help us decide how to traverse the graph. So we started by pushing one object on there. I called it a city block because that's essentially what we were dealing with, starting with a heat loss 0, row column, etc. count of 0. The instruction said the first 0, 0 does not count against your heat loss. We push that onto the queue, and then we loop through the priority queue of length as long as the length is greater than 0. At each location we pop, or each iteration rather, we pop the lowest record off the heap. Let's look at our heap implementation. So we did have to implement a heap. We could have done something with like a slice of ints, but I didn't really want to go that route. So I implemented a couple of methods. In Go, the heap just has a heap interface, and in order for you to initialize the heap and the heap to be maintained, you have to implement a structure with those methods. It's like len for the length, less, swap, push, and pop. Those are the methods that were necessary to implement. So I walked through that. Once that was done and we have our heap situated, we can then walk through this in priority queue fashion. So we prioritized anything with a lower number, as the next in queue. And as we traverse this graph, so for instance, we start at 0. This would have a heat loss of 4. This would be a heat loss of 3. They both would be queued at the same time. And then on our next iteration, when we popped off the queue here, we would grab the one with the lower heat value. So in this case, it would be the 3. It then would look at the 2 and assign the accumulative heat loss value of the 3 we had here plus the 2, which would be 5. And the same thing here, the 3 with 3, which would be 6. So then on the queue, the priority queue, we then had a heat loss of 5, a heat loss of 6, and a heat loss of 4. So the next one off the stack would be this one. So a heat loss of 4, we would go here to 5 and here to 6. And we would crawl in that manner all the way down, prioritizing the lowest cost to get to the bottom here. I suppose we could, if we found a cheaper way to get here, do some sort of modification of the queue. It may not really save us any time. So this was performant enough. As you can see, we ran both in under a second, part 1 and part 2. So that's pretty much it as far as the heap is concerned. We started with a couple of guarding clauses that if our row and our column got outside our range, to return the heat loss that we were at, the cumulative heat loss of that city block. For part 2, we did add a minimum. So the requirement was you had to have a minimum amount of blocks to get to the end. And so that was added here. We created a visited map and just stored everything as a string for the keys. And then we ranged through our different sets of directions. So you've got right, left, down, up, and we would iterate through those, and we would augment the direction accordingly. We wanted to make sure we didn't break out to a direction that didn't exist. So guard clause here. There was also a rule that stated that we could not go in reverse. So that's what this rule here is for. We then, each time we processed, we had another rule that said we could not go more than X in the same direction. So that was part of part 1. So if our directions are the same, then we increment our count. And if our count is over our max, initially this was hard-coded to 3, it's over our max, then we continue. We can no longer go in that direction in a turn of either a left or a right, or a 90-degree turn is necessary. And then finally, there was this requirement we saw above for part 2, the minimum. So if we are below our minimum count, we weren't allowed to turn. And so we continue. There was one condition where, since we started 0, 0, we had to define that here because the count was always 0 at position 0, 0. So that's how we handled that. If all those conditions are met or not met, those guard clauses, then we add to the heap, we push onto the heap, and that brings us into the next loop, which we then prioritize based on the heat loss. Every time we add that record, we always add the heat loss of the new row, new column, and that's how we get those values, and we traverse this map problem. This is a very exciting one today. I know for me personally, I've not implemented Dijkstras. I've not had a requirement or a need to. And so this was kind of new territory for me. But walking through it, this is what makes Advent of Code so amazing, is that it pushes us beyond the barriers that we live in. It pushes us beyond our boundaries and grows us into better developers, better engineers. That's all I have for today. Over and out.